Hello again, Year 9. Welcome to Lesson 3. This is our Week 11 work and should see us out to the end of the term. Now, we're going to continue to have a look at atomic structure here, but specifically, we're going to have a look at this idea of electron shells. The fact that the electrons in an atom orbit the nucleus in layers. Now, in a previous lesson, I discussed how this works for two elements that I've redrawn over here. So let us recap so we're all up to speed. So what is here is a helium atom. Now helium has an atomic number of 2, which we get from the periodic table. So that tells me that helium is going to have 2 protons and 2 electrons. So that's what I've drawn. Now the thing is, helium has electrons orbiting in the first layer. It doesn't actually have a second layer of electrons because it doesn't need one. And I'll explain why. You see, the first layer of electrons always has a maximum capacity of 2 electrons. And helium with 2 electrons just fills up that first shell quite evenly. It's, like I said in a previous lesson, a very nice fit. Now, the second atom that I covered in another lesson was lithium. Now, lithium here has 3 protons and 3 electrons, so it must have atomic number 3 on the periodic table. Now, the thing is, lithium actually has 2 electron shells, as shown by these black circles. The X's represent the electrons. Why? Because, as I've discussed previously, the maximum number of electrons that the first shell can hold is 2. So what lithium has to do is put its third electron in its second shell of electrons. Okay? So we've already covered that. But we're going to explore this idea further by looking at other elements, other atoms of other elements, and understanding, well, how do they have their electrons arranged in shells? And there's a few little rules here we need to remember. And the first rule is, like I've said before, the first shell always contains a maximum of 2 electrons. So I'm going to clarify that a little bit further with my first example here, which is the element hydrogen. Now, hydrogen is not only just the smallest element in the universe, it's the most abundant element in the universe. So if I was going to take a tally of all the atoms in the universe, I'd find that the overwhelming majority, super duper majority, is hydrogen. It's very small and there's lots of it. Now, if I have a look at the tile, the symbol for hydrogen on the periodic table, I'm going to notice a couple of things. First of all, I'm going to notice it's got an atomic number of 1. So therefore, it's got 1 proton and 1 electron. The other thing you might notice is its atomic mass is very close to 1, very close to 1. What that means is most hydrogen atoms are just a proton in the nucleus, no neutrons at all. Now, some hydrogens do have neutrons in the nucleus, and that's why the average mass for every hydrogen in the universe is a little bit above 1. But it's still very, very close to 1. So it tells us that, well, most hydrogen atoms are just a single proton and a single electron. So what I've done over here is I've started to draw the model of a hydrogen atom. Now remember, I've said I'm not going to draw any neutrons. I don't have to, because your average hydrogen atom isn't going to have any neutrons. But what it is going to have is, like I said before, 1 proton. So let's add that to the nucleus now, 1p. So my nucleus is really just 1 particle, 1 single proton. But it still has an electron, and like every other atom, that electron orbits the nucleus. Now, keep in mind, our first shell contains a maximum of 2 electrons. Hydrogen only has 1. So it doesn't quite fill its first shell. We just stick 1 electron in the first shell and we're done. We've just drawn a beautiful model of a hydrogen atom. So let's go into larger elements and understand how we approach these now. Now, fluorine's a little bit like the lithium example that I've done. I'll clarify why later, but let's have a look at the nucleus of fluorine first. Now, the atomic number is 9, so that means 9 protons. So let's put that in the nucleus now, 9p. Now, in a previous video, I said that you calculate neutron number by subtracting this number, the mass number. Oh, I'm sorry, my mistake. You subtract this number, the atomic number, from the mass number. So if we want to know the number of neutrons, we have to do 19 minus 9. Easy, 10. So I write 10 N over here in my nucleus. So what we'd expect is most fluorine atoms to have 9 protons, 10 neutrons in the nucleus. Now, the last thing we have to do for fluorine is the electrons. So how many electrons does it have? Well, the atomic number tells us that it is going to have 9. But just like these two elements here, it's going to have to follow the rules for how many electrons can fit in each shell. So, 2 in the first shell. It is always the case because the inner shells will fill up first. They always fill up first. They never skipped. So we'll take 2 of fluorine's electrons and put them in the first shell. So we've taken away 2. We're left with 7. What do we do with the 7? Well, they'd have to go in the second shell. Now, is there enough room for the electrons in the second shell? Well, yes, because the maximum capacity of the second shell is 8. 8 electrons. So with 7 electrons left to put in a shell, there's enough room in the second shell for fluorine to have 7 electrons. So I'm going to add those 7 electrons now, kind of like this. All right, so I'll make sure I've done it right. 1, 2 in the first shell, and 1, 2, 3, 4, 5, 6, 7 in the second shell means I have my total of 9 electrons. So there we are. We've finished the model of the fluorine atom. Correct with protons, correct with neutrons, and correct with electrons in their individual shells or layers. All right, so my last example for this part is a much bigger atom. Still kind of small, it's number 11 on the periodic table, and some of the atoms go up to 118 on the periodic table. So it's still quite small, but much bigger than the atoms we've drawn so far, so I better be careful. So it is sodium. I've spoken about this metal before. Now, 11 is the atomic number, so let's go and write the number of protons in the nucleus now. 11p. All right, let's do our neutron number. Neutron number is atomic number subtracted from the mass. We've got to round up the mass first, so let's round this 22.99 to 23. 23 minus 11 gives us 12. So I better go and put 12N in my nucleus to indicate that most sodium atoms have 12 neutrons. All right, so that's out of the way. Now my final concern is, what do I do with the electrons? Well, it's just as I've done with the previous atoms. I need to remember that the inner shells will fill up first. The first shell contains 2, the second shell can contain 8. I've got 11 in total, so if I put 2 in the first shell, and if I put 8 in the second shell, which I'm about to do, I'll be left with 1 I need to do something with. So I'll draw the 8 electrons in the second shell. There we go. And of course, that only counts for 10 electrons. I have 1 electron remaining. Can't go in the second shell because the second shell is already full with 8 electrons. It's not going to take any more. So what sodium has to do is it has to force its 11th electron into a third shell, which makes the atom even bigger than lithium, because the more shells you have, the bigger the atom is going to be. Now, do I have it right? 2 in the first shell, plus 8 in the second shell, plus 1 in the outer shell, goes up to 11. Now, let me conclude by saying this third shell has a capacity of 8 electrons. So if I did have to keep adding electrons to my third shell, I could go up to a point where I've got 8, and then I'm going to run out. Well, in that case, I'm going to have to go into a fourth shell. And if I was going to draw something like potassium or calcium with atomic numbers of 19 or 20, yeah, I'm going to have to go and draw myself a fourth shell. Now, luckily for us at year 9, we will never have to draw anything beyond potassium or calcium. We'll never have to draw anything larger than element 20. So that's going to keep it nice and simple for now. And all you need to do is remember this 2-8-8 rule. 2 electrons in the first shell, 8 electrons in the second shell, 8 electrons in the third shell, and the inner shells will always fill up first.